Hello everyone, I am Anisha Sarma from Namchi Government College, bearing roll number 18NS0010. I am here to make a video for the partial fulfillment of BSc Honours on Physics 6th semester, February to July 2021. Before starting my video, I would like to extend my heartily gratitude to Department of Physics, Namchi Government College and Dr. C.P. Khatiwara sir for giving me such a wonderful platform to make this video. This video carries 25 marks instead of 25 marks practical examination. So without any further delay, let us begin our today's video. So today I am going to discuss about Einstein and Debyes theory in this video. My topic for this presentation is Einstein and Debyes theory for specific heat of solid. So now let us see what is specific heat of a solid. Specific heat of a solid is denoted by Cv. It is defined as the change in internal energy with respect to temperature at a constant volume. Mathematically, Cv is equals to del E by del T at a constant volume V. So before Einstein and Debyes theory, there was a classical theory which was also known as Dulong's Petit law. This law states that the specific heat Cv is independent of temperature. It is equal to 3R at high temperature and also at low temperature. This is the graph between specific heat Cv and temperature. It showed that the specific heat is equal to 3R at high temperature and low temperature. Classical theory failed to explain that why in the low temperature range the specific heat Cv of all solid is found to 0. According to the classical theory of specific heat of the solids, the atoms in a solid were considered as simple harmonic oscillators vibrating independently and having continuous energy between 0 and infinity. The discrepancy in the classical theory of specific heat was investigated by Einstein in 1906 by applying the Planck's quantum theory. So, this is the experimental curve between specific heat and the temperature. It showed that the specific heat is equal to 3R at high temperature, but it lowers with lowering in temperature. So Dulong's Petit was not able to explain why specific heat tends to 0 at low temperature. So this was the discrepancy in the classical theory. So the discrepancy in the classical theory of specific heat was investigated by Einstein in 1906 by applying the Planck's quantum theory. So now let us see the assumptions of the Einstein theory. Assumptions of the Einsteins was same as Dulong's Petit theory, but one assumption was different. So now let us have a look at the assumptions of the Einstein theory. The main features of the Einstein theory of specific heats are all the atoms in the solid are independent harmonic oscillator. He assumed that all the atoms in the solid are independent harmonic oscillator, and Dulong Petit too assumed the same. Each atom, that is oscillator, has 3 degrees of freedom. So each atom, that is one atom, has 3 degrees of freedom. So their n accelerators have 3n degree of freedom. So n number of atoms has 3n degree of freedom. All the atoms vibrate with same natural frequency nu. So the assumptions of to here was same as the assumptions of Dulong's Petit law, but the another assumption is different. In classical theory, they assume that energy is continuous and it's from 0 to infinity, but in Einstein theory, he assumed that energy is discrete. He assumed that E dash is equals to n plus 1 by 2 h nu. So let us consider this as equation number 1. So according to Maxwell-Boltzmann distribution law, the average energy of the harmonic oscillator is given by U bar is equals to summation of n is equals to 0 to infinity U dash exponential minus of U dash by kt whole divided by summation of n is equals to 0 to infinity exponential minus of u dash by kt. This is our equation number 2. So now using this equation number 1 and 2, we get that u bar is equals to summation of n is equals to 0 to infinity. In place of this u dash, we can write n plus 1 by 2 h nu exponential minus of n plus 1 by 2 h nu by kt whole divided by summation of n is equals to 0 to infinity exponential minus of n plus 1 by 2 h nu by kt. Let minus of h nu by kt is equals to x. This is our equation number 4. So we assume that minus of h nu by kt is equals to x. So now using this equation number 4 in equation number 3, we get that u bar is equals to h nu. Taking this h nu outside, we get that summation of n is equals to 0 to infinity n plus 1 by 2 exponential n plus 1 by 2. In place of this minus of h nu by kt, we can write x whole divided by summation of n is equals to 0 to infinity exponential n plus 1 by 2. In place of this minus of h nu by kt, we can write x. So now we can put the value of n, that is n is equals to 0, n is equals to 1, n is equals to 2 and so on. But here we are considering only 3 terms of n, that is n is equals to 0, n is equals to 1 and n is equals to 2. So here in this equation, putting n is equals to 0, we get 1 by 2 exponential 1 by 2 x and divided by exponential 1 by 2 x. If we put n is equals to 1, we get 3 by 2 exponential 3 by 2 x divided by exponential 3 by 2 x. If we put n is equals to 2, we get 5 by 2 exponential 5 by 2 x exponential 5 by 2x. So we know that this exponential 1 by 2x can be written as e to the power of x by 2. So u bar is equals to h nu 1 by 2 e to the power x by 2 plus 3 by 2 e to the power 3x by 2 plus 5 by 2 e to the power 5x by 2 plus so on. We can write exponential terms in the e to the power of x term. So whole divided by e to the power x by 2 plus e to the power 3x by 2 plus e to the power 5x by 2 plus so on. So if we look here clearly, we can see that this e to the power x by 2, if we differentiate this term, we can get 1 by 2 e to the power x by 2. We know that dx of e to the power of ax is equals to a e to the power of ax. So if we differentiate e to the power x by 2, we get 1 by 2 e to the power x by 2. So we can say that this is our function f. This is our function fx, and we can see that if we differentiate this function, we get this. So this is our fx and this is our f dash x. So we know that f dash x by fx is equals to d by dx of log of x. So u bar is equals to h nu d by dx log of, in place of x we have e to the power x by 2 plus e to the power 3x by 2 plus e to the power 5x by 2 plus so on. So u bar is equals to h nu d by dx of log, if we took e to the power x by 2 common, we get bracket 1 plus e to the power of x plus e to the power 2x plus so on. So u bar is equals to h nu d by dx of, so looking at this term clearly, we see that it is in the form of log a into b. So we know the formula for log a into b, that is log a plus log b. So u bar is equals to h nu d by dx of log a plus log b. Log a, log e to the power x by 2 plus log 1 plus e to the power of x plus 1 plus e to the power 2x plus so on. U bar is equals to h nu d by dx of, we know that this log and e gets cancelled out, so x by 2 plus log 1 plus e to the power of x plus e to the power 2x plus so on. This is our equation number 5. Now log 1 plus e to the power of x plus e to the power of 2x plus so on is equals to minus of log 1 minus e to the power of x. This is our equation number 6. So now using equation number 6 and 5 we get u bar is equals to h nu d by dx of x by 2. This plus and this minus equals to minus log 1 minus of e to the power of x. U bar is equals to h nu. Now differentiating this we get d by dx of x by 2. Differentiating this we get this x equals to 1 and 2 will be 2 minus of, now again differentiating this term we get 1 by 1 minus of e to the power of x, and differentiating this term we get 1 is equals to 0 and minus of e to the power of x. U bar is equals to h nu 1 by 2. This minus and this minus gives plus e to the power of x by 1 minus of e to the power of x. So here u bar is equals to h nu 1 by 2 plus dividing by e to the power in this term. Dividing by e to the power in x in this term we get e to the power of x by e to the power of x divided by 1 by e to the power of x minus of e to the power of x by e to the power of x. This e to the power of x and this e to the power of x get cancelled, and this e to the power of x and this e to the power of x get cancelled. So u bar is equals to h nu 1 by 2 plus 1 by this e to the power of x. When we take this up, we get 1 by e to the power minus of x minus of 1. U bar is equals to, multiplying by h nu inside this bracket, we get h nu by 2 plus h nu by e to the power of minus, in equation number 4, we assume that x is equals to minus of h nu by kt. So putting the value of x, we get e to the power minus of minus h nu by kt minus of 1. U bar is equals to h nu by 2 plus h nu by e to the power minus into minus gives plus h nu by kt minus of 1. Equation number 7. So now if we put t is equals to 0 in equation number 7, this whole terms is equals to 0. So only the term left behind is u bar is equals to h nu by 2. So the first term in equation number 7 is called 0 point energy, h nu by 2, and it's independent of temperature. Thus vibrational energy is not 0 at absolute 0 temperature. So putting t is equals to 0 in equation number 7, we get that u bar is equals to h nu by t. Now total vibrational energy of anharmonic accelerators having 3 degrees of freedom is u be the total vibrational energy of anharmonic accelerators having 3 degrees of freedom is 3 into u bar. So u is equals to 3 u bar is equals to h nu by 2 plus h nu by e to the power h nu by kt minus of 1. Multiplying by h 3n inside the bracket, we get u is equals to 3n h nu by 2 plus 3n h nu by e to the power h nu by kt minus of 1. Now we know that Cv, specific heat, is equals to du by dt. Cv is equals to d by dt. Putting the value of u, we get 3n h nu by 2 plus 3n h nu by e to the power h nu by kt minus of 1. So this term will not get differentiate because it is constant. Okay, so Cv is equals to d by dt 3n h nu e to the power h nu by kt minus of 1. This term doesn't get differentiate because here is no any term t, so it is equals to 0. Cv is equals to d by dt 3n h nu by e to the power h nu by kt minus of 1. Cv is equals to taking 3n h nu outside the bracket because it is constant, 3n h nu d by dt 1 by e to the power h nu by kt minus of 1. So here we need to differentiate this term, so we can assume this as u and v. So now using u by v rule, we know that u by v is equals to v du by dt minus of u dv by dt whole divided by v square. So Cv is equals to, first we need to write v, first Cv is equals to 3n h nu. So now v e to the power h nu by kt minus of 1, d dt of 1 is equals to 0, minus of u 1. Differentiating v, we get e to the power h nu by kt minus of h nu by kt square minus of 0 whole divided by e to the power h nu by kt minus of 1 whole square. So this term, these whole terms will be 0. So Cv is equals to 3n h nu 0 plus h nu by kt square e h nu by kt whole divided by e to the power h nu by kt minus of 1 whole square. So now multiplying and dividing by k on RHS, we get that if we multiply by k, here it will be 3n k h nu and here will be k square. So Cv is equals to 3n k. This h into h is equals to h square and nu into nu is equals to nu square. So k square t square. So we can write Cv is equals to 3n k h nu by kt whole square e to the power h nu by kt divided by e to the power h nu by kt minus of 1 whole square. This is our equation number star. So let h nu by k, we assume that h nu by k is equals to theta e. Theta e is equals to Einstein temperature. So putting this value in equation number star, we get Cv is equals to 3n k, h nu by k is equals to theta e by t whole square exponential e to the power h nu by kt. We can write this in the form of exponential theta e by t divided by exponential theta e by t minus of 1 whole square. This is our equation number 8. So now let us consider the following cases. Case number 1. At high temperature, T is greater than theta e. This implies that theta e is less than t. Dividing by t, we get theta e by t is less than 1. As exponential of theta e by t, if we expand this term, we get 1 plus theta e by t plus 1 by 2 theta e by t whole square plus so on. So exponential theta e by t is equals to 1 plus theta e by t. This is our equation number 9. We are neglecting higher power here because we know that theta e is our small quantity. So the power of the small quantity results much more and more lesser quantity. So we are neglecting the higher power. So now using equation number 9 in 8, we get that Cv is equals to 3n k theta e by t whole square. In place of exponential theta e by t, we can write 1 plus theta e by t divided by 1 plus theta e by t minus of 1 whole square. This minus of 1 and this plus of 1 gets cancelled. Then we get Cv is equals to 3n k theta e by t whole square 1 plus theta e by t divided by theta e by t whole square. This theta e by t whole square and theta e by t whole square gets cancelled out. So Cv is equals to 3n k 1 plus theta e by t. So as t tends to infinity, then theta e by t tends to 0. So we can say that Cv is equals to 3n k 1 plus 0. Cv is equals to 3n k, where n is equals to Avogadro number, k is equals to Boltzmann constant. So multiplying these two terms, we get gas constant. Cv is equals to 3 of R. So in higher temperature, Cv is equals to 3R, which is same as Dulong's Petit law. So now at low temperature, when T is less than theta e is greater than T, then exponential theta e by t minus of 1 is equals to exponential theta e by t. As theta e is greater quantity, so we can neglect this minus of 1. This is our equation number 10. So now in equation number 8, we can write that Cv is equals to 3n k theta e by t whole square exponential theta e by t, we are neglecting minus of 1, divided by exponential theta e by t whole square. Cv is equals to 3n k theta e by t whole square. So here exponential theta e by t divided by exponential 2 theta e by t, because we know that we can write e to the power of x whole square is equals to e to the power of 2x. So we can write this exponential theta e by t whole square as exponential 2 theta e by t. Cv is equals to 3 n k theta e by t whole square. So we know that if we have e to the power of x by e to the power of 2x, we can write it as e to the power of x minus of 2x is equals to e to the power of minus of x. So in the same way, here we can write exponential of minus of theta e by t. This is our equation number 11. Thus, equation number 11 shows us that Cv decreases exponentially. Cv decreases exponentially as Cv is directly proportional to exponential of minus of theta e by t. So now let us see the limitation of Einstein theory. At low temperature, Einstein curve deviates from the experimentally observed value. So here we can see that the Einstein curve deviates more than the experimental curve. So this was the limitation of Einstein theory. The discrepancy between the theoretical result and experimental result was assumed to be more oversimplified model employed by Einstein. According to Einstein theory, all the atomic harmonic accelerators vibrate independently with same frequency. So already in assumptions we see that Einstein assumed that all the atoms accelerate independently with same frequency. In reality, the vibrations of a particular atom must be very complex as each atom is in a solid is under the influence of field of force of thousands of other vibrating atoms, since the vibrations cannot be considered independently. Hence, we can say that there is a range of possible values of vibrational frequency instead of just a single frequency for all the atomic accelerators. So, this was the limitation of Einstein theory. So, after the Einstein theory, Debyes theory came forward. So now let us see Debyes theory of specific heat. The main assumption of the Debyes model of specific heat of solid are as follows. In Einstein theory of specific heat of solids, each atom is supposed to vibrate as a single harmonic accelerators independently of its neighboring atoms. We already saw that Einstein assumed that all atoms vibrate independently. But the limitation is not so simple because each atom is under the influence of field of other vibrating atoms. Debye took into account the effect of coupling between neighboring atoms and considered the body as a continuous elastic body. So he considered that the solid as a continuous elastic body. According to Debye model, elastic standing waves are produced due to vibrations of atoms. He assumed that due to the vibration of atoms, there will be the standing waves. There will be two types of waves produced, transverse waves and longitudinal waves. He also assumed that the energy of these elastic standing waves was not continuous but quantized. The total number of the vibrational modes are limited to 3n, where n is equals to Avogadro number is equals to 6 into 10 to the power of 23 is equals to number of atoms present in 1 mole of substance. There is a certain frequency nu d. He also assumed that a certain frequency nu d called Debye frequency above which no vibration takes place, and this frequency nu d is common to both longitudinal and transverse waves. So number of the modes transverse plus longitudinal in the frequency range is equals to nu to nu plus d nu are given by. So for transverse wave and longitudinal waves, the frequency range is nu to nu plus d nu, and the number of modes is given by 4 pi v nu square d nu by v t cube plus 4 pi v nu square d nu by v cube L. So here we see that this term is multiplied by 2. So this is the transverse wave, and the number of modes in transverse wave is higher than that of the longitudinal wave. So this is our equation number 1. So in equation number 1, V is equals to volume of solid, Vt is equals to velocity of transverse wave, and Vr is equals to velocity of longitudinal waves. So Taking 4 pi v common, we get 2 by v t cube plus 1 by vl cube into nu square d nu. Total number of modes, we get total number of modes by integrating this term. So integration of 4 pi v 2 by vt cube plus 1 by vl cube nu square d nu. So total number of modes is equals to 3n. 3n is equals to, taking 4 pi v 2 by vt cube plus 1 by vl cube constant, we get integration of 0 to nu d nu square of d nu. So cross multiplying this with this, we get 3n by 4 pi v 2 by vt cube plus 1 by vl cube is equals to integration of nu square d nu is equals to nu cube by 3 limit 0 to nu d. So now multiplying this and this, we get 9n by 4 pi v 2 by vt cube plus 1 by vl cube is equals to limit, upper limit minus lower limit, that is nu d cube minus of 0 cube. So 9n by 4 pi v 2 by vt cube plus 1 by vl cube. So this 3, while taking, if we take this 3 this side, it will be 1 by 3 is equals to nu d. Average energy of the oscillator having frequency nu at temperature T is given by, so now we are going to find out average energy of the oscillator whose frequency is nu and temperature is T. U bar is equals to h nu by exponential h nu by kt minus of 1. This is our equation number 2. Total vibrational energy of the solid is given by, total vibrational energy U is given by integration of U bar into number of modes in frequency range nu to nu plus d nu. So U is equals to limit 0 to nu d. So U bar is equals to h nu by exponential h nu by kt minus of 1 into number of modes in frequency range nu to nu plus d nu is equals to 4 pi v 2 by vt cube plus 1 by vl cube nu square d nu. U is equals to, we can take this 4 pi v 2 by vt cube plus 1 by vl cube outside because it is constant term. We can take this as also outside, it is also constant. So now integration of 0 to nu d nu cube by exponential h nu by kt minus of 1 d nu. This is our equation number 3. As nu d, we know that nu d is equals to 9n by 4 pi v 2 by vt cube plus 1 by vl cube to the power 1 by 3. We have found this above, so we can write this here. So now cubing this, we get nu d cube is equals to 9n by 4 pi v 2 by vt cube plus 1 by vl cube. So again cross multiplying this, we get 4 pi v 2 by vt cube plus 1 by vl cube is equals to 9n by this will go here. So nu d cube. This is our equation number 4. So using equation number 4 and 3, we get u is equals to, so in place of this term we can write 9n by nu d cube h integration of 0 to nu d nu cube by exponential h nu by kt minus of 1 d nu. This is our equation number 5. Let h nu by kt is equals to x is equation number 6. We assume that h nu by kt is equals to x. This is our equation number 6. So when nu is equals to nu d, then x is equals to xm. So h nu d by kt is equals to x of m. So this is our equation star. So nu is equals to kt x by h. This is our equation number 7, and d nu is equals to kt by h dx is equals to equation number 8. So now using equation number 6, 7 and 8 in equation number 5, we get that u is equals to 9 and h by nu d cube integration from 0 to x1. We are changing limit here because we are using everything in the terms of x. So 0 to x and here nu cube. Nu is equals to ktx by h. So nu cube is equals to ktx by h cube divided by exponential h nu by kt is equals to x minus of 1 and d nu is equals to kt by h dx. So this h and this h gets cancel out. So u is equals to 9n by nu d cube kt by h whole cube kt integration of 0 to xm x cube by exponential x minus of 1 dx. So here we can take this kt by h outside. This is constant term. This is also our constant term. So we took out this outside. So u is equals to 9n kt into kt by h nu d cube. So this is our whole cube 0 to xm x cube by exponential x minus of 1 dx. This is our equation number 9. So let h nu d by k is equals to theta d. This is our equation number 10 where theta d is the Debye temperature. So from equation number star we can write that theta d by t is equals to xm. This is our equation number 11. So from equation number 9 and 11 we get u is equals to 9 and kt t by theta d whole cube integration from 0 to theta d. So we are changing the limit from 0 to theta d by t x cube by exponential x minus of 1 dx, equation number 12. So now let us consider following two cases. At high temperature, t is greater than theta d. Theta d is less than t. So we can say that theta d by t is approximately equals to x, which is less than 1. So now exponential of x minus of 1. So if we expand this, we get 1 plus x square by 2 factorial plus so on, and this minus of 1 will be minus of 1. So exponential of x minus of 1 is equals to 1 plus of x. So we are neglecting this term, minus of 1. Exponential x minus of 1 is equals to x, equation number 13. So now using equation number 13 in 12 we get u is equals to 9n kt t by theta d whole cube integration of 0 to theta d by t in x cube by x dx. So this x and x cube cancel out. So u is equals to 9n kt t by theta d whole cube. This is x squared. This will be x square. So integrating this term we get x cube by 3 limit 0 to theta d by t. U is equals to 9n kt t by theta d whole cube into 1 by 3 putting limit theta d by t whole cube. So this 3 and this 9 cancel out, and this and these terms also gets cancelled out. So now we get that u is equals to 3n kt. U is equals to 3 RT. So we get that u is equals to 3n kt. So we can write that u is equals to 3 RT. Cv is equals to du by dt. We know that Cv is equals to du by dt. So d by dt of u is equals to 3RT. So Cv is equals to 3R. At high temperature, Cv is equals to 3 of R. So now case number 2, that is at low temperature, T is less than theta d. This implies that theta d by t is approximately equals to infinity. So from equation number 12 we can write that u is equals to 9n kt by t by theta d whole cube. So limit 0 to infinity x cube by exponential x minus of 1 dx. U is equals to 9 and k. This t cube and t gives t to the power of 4. Theta d to the power of 3 into, so this term, this is our special integration, and so integrating this term we get x to the pi to the power of 4 by 15. So now we know that specific heat Cv is equals to du by dt is equals to d by dt. In place of u we can write 9 and k t to the power of 4 by theta d to the power of 3 into pi to the power of 4 by 15. Cv is equals to 9 and k by theta d to the power of 3 pi to the power of 4 by 15 d by dt of t to the power of 4. So this and this gets cancelled. So Cv is equals to 3 and k pi to the power of 4 divided by theta d to the power of 3 into 5. So in differentiating this we get 4t cube. So Cv is equals to 4 into 3 is equals to 12 and k pi to the power of 4 by 5 theta d to the power of 3 t cube. So here we find that Cv is directly proportional to this t cube. This is well known Debye t cube law and is good agreement with experimental data. So the Debye's law showed that the specific heat Cv is equals to 3R at high temperature, and Cv is directly proportional to temperature. So Cv decreases with temperature. So we can see graph between the Cv and T. So this is our specific heat and this is our temperature. So according to DeLong's Petit law, we found that the specific heat Cv is equals to 3R at high temperature and also at low temperature. According to Einstein curve, we found that specific heat Cv is equals to 3R at high temperature, but it decreases exponentially at low temperature. But the experimental curve showed that it decreases with decrease in temperature. So Debye's curve also showed that it decreases with temperature. So the experimental curve and the Debye's curve is equal. So Debye found that Cv decreases with temperature. So limitations of Debye's law. So talking about the limitations of Debye's law, limitations were as follows. Since velocities of t and l, that is transverse and longitudinal waves, are different, hence Debye cutoff frequency nu d should be different for these two waves. The contributions of electrons to the specific has been totally ignored. The theory doesn't apply to crystals have more than one type of atoms like NaCl. So the theory applied to the crystals having only one type of atoms, but it doesn't apply to crystals having more than one types of atoms like NaCl. Theta d, which is assumed to be independent of temperature, has been actually found to vary with temperatures. So this is the limitations of Debye's law. So thank you so much for watching my video.